Hi everyone, my name is Mihael Liskij and today I'll be presenting to you TEP pair, a paper I have worked on with colleagues Ivo Sluganovic and professors Ante Zurich and Ivan Martinovic. Now first of all, I assume many of you already tried virtual reality at some point, but for those of you who are not familiar with it or with augmented reality, I'm going to just give a brief introduction to it. So here on this screen we see a tablet which is showing some 3D scene. But the thing is, it's actually overlaying a 3D model of the trees over a real-life 3D model of the building. And basically this is what AR is. We're augmenting the real world with the virtual world. Now, this format on the tablet is not that practical, and as the technology advanced, we got AR headsets, which basically work in a way that they show an individual image, one on the left, one on the right eye, in a way that the person sees a hologram in the real world. And these are the two most probably famous examples. So we have Magic Leap 1 and the HoloLens 2. Some famous people like Mark Zuckerberg and the Apple CEO Tim Cook both mentioned in their interviews this year that we expect a breakthrough in AR technology in the following decade. And what they both put focus on in their interviews are the shared experiences that we can have with AR devices. Now, what does that basically mean is we can have a room of people who are all sitting around the desk in this example, and they all see the same hologram on their screens at the same time and at the same position. Now, this enables many different applications. For example, if you had med students who are trying to learn about the human body, we could have a model of the human, and the instructor could point at some specific point, and all the students will see the exact point he's pointing at. Now, in all of these settings, we think it's crucial to be able to establish a secure peer-to-peer connection between devices. So our goal for this paper was to design an extremely easy to use authentication protocol, which requires no new gestures. And there is already some limited related work in this area. So two papers we have Looks Good to Me and the HoloPair paper, but both have some drawbacks. In the first case, Looks Good to Me paper required some technology which is not yet possible to use on the current devices, while in the case of HoloPair, it required the users to do complicated gestures. And now, what our solution is, what we try to achieve is that we wanted a protocol which allowed users to just look at each other and do a tap. And I'm going to explain what a tap is shortly, but basically what we get from here, that is a shared secret that we can use as a password for a standard ACM protocol. So how does TEP pair actually work is we're going to adapt a Password Authenticated Key Exchange protocol to use spatial secrets as the password. And now we devise two ways on how to generate those spatial secrets. One is going to be a line, and the other one is going to be the point. Before going into further details on how we actually create those spatial secrets, I'm just going to briefly explain how AR devices perceive the world. In our case, we were using the HoloLens device, which has multiple depth sensors at the front of it. Now, as you walk through the room, the depth sensors are going to map out the room and is going to create a 3D representation of it. Now, what this allows is basically creating a spatial anchor, which is a representation of a 3D point in a room. And now, at some later point, if the device scans the room again and gets the same 3D representation of it, it's going to be able to locate the same spatial anchor. And this works across multiple devices. So if we had two HoloLens devices, on one we could store the spatial anchor, transfer it to another device, and then it could again find the same spatial anchor. And what's important here is this allows us to create a shared coordinate system. Another feature of the HoloLens device, which is pretty important, is head tracking and hand position tracking, which basically allows the user to gaze at some point in the room and then do a tap in the air. Basically, they put their index finger up and do a click action similar to clicking a mouse. And the device is going to register that, and we can register the point at which the user clicked. In our system model, we assume two collocated users. So we have a user A and user B, both of which are wearing an AR-enabled device. We also assume the existence of two channels. One is the wireless channel, which allows us to transfer large amounts of data, and another is the gaze channel, which basically means that the devices can use the users to select a point in the room. We also assume that there are no pre-shared secrets or that we have trusted third parties, and we also have to assume that the users cannot take off their headsets. For our adversary, we assume that he completely controls the wireless channel and that he knows the spatial mapping of the environment, that is the room in which the protocol is taking place, but that he is unable to observe the communication between the two users. Now the question is, how do we actually establish a spatial secret between two devices? In the first step, one of the devices is going to choose a spatial anchor, and in the next step, it's going to send it over the wireless channel to the other device. The other device can then find the spatial anchor, and after the first two steps, we have a shared coordinate system. In the third step, we're going to ask the users to look at each other. What this does is basically allows us to use the line which is going through the devices as the spatial secret. Another way that we can establish a shared spatial secret is, again, in the first two steps we establish the shared coordinate system, but then in the third step we're going to ask the users to select the same point in the space. And this is again possible because we have a shared coordinate system and both users are going to select the same point. There are multiple challenges in actually establishing a shared spatial secret. One of them is that user and position tracking is not perfect. And even if we manage to solve that, how much entropy do we actually get from the shared spatial secret? To solve the precision problem, we opted to use an error correction method used in picture passwords. In picture passwords, the users are expected to click on multiple points in succession to authenticate themselves. Now, it's unreasonable to expect the users are going to be able to click the exact pixel they need every time. So what we're going to do is we are going to accept all pixels which are close enough to the target pixel. More formally, what we're going to do is define a security parameter R, which basically says that we want to accept all points which are around the target point as correct, and then discard all the others as incorrect. Now we're going to look at how we can apply the error correction method to the SecretLine shared secret. First of all, we're going to generate a circle which contains the whole room and is publicly known. Then we're going to look at the line going through the first device. The line is going to intersect the circle at 2 points, of which we're going to record the x and y coordinates. We are ignoring the z coordinate because we assume the adversary knows the heights of the users, so it would be pretty easy for him to guess the third coordinate. From those 2 points, we record them as a 4D coordinate and then do the same thing for the second device. Now we have 2 4D coordinates, and we can say that we're going to accept all secrets that are in a 4D sphere of radius r around the first 4D coordinate. The secret point error correction is a bit simpler. In this case, when the user selects a point, we're just going to record the 3D coordinates of it. And then we say we accept all other points which are in a sphere of radius r around the target point. On the right, we can see some measurements where we recorded the point selections from multiple positions in a room. In this case, there was a point on the wall, and then we can say we're going to accept all points which are in a 3D sphere around the target point. There are 3 main factors which can influence the precision of our device. In the first case, the position tracking, it was found out in some other paper that we can expect a hologram drift of around 6 mm. For the other 2 cases, we had to do some of our own measurements and try to approximate the error because of them. And we found out that we can expect around 4 mm of impreciseness in addition to the hologram drift on top of it. For our setup, we used 3 rooms. One of them is an office, the other one is a kitchen, and the third one is a classroom. And those are some of the settings we expect a pairing protocol to take place in. In general, in our experiments, we decided to record pairing attempts and then use simulations to try to approximate the probability of successful pairing depending on how we changed our security parameter. Basically, if the security parameter was larger, that is, we accepted more points around the target point, we would see that the probability of successful pairing would go up, while, because we are accepting again more points, we expect the entropy to go down because the adversary has an easier time of guessing the target point. We see here that for the SecretLine simulation, we can expect, if we take a security parameter of 5 centimeters, we could expect around 90% probability of successful pairing, while we would expect around 11 bits of entropy. That would be equivalent with around a 3-digit pin. For the secret point experiments, we did basically the same thing. For the different rooms, recorded multiple pairing attempts, and then did a simulation to see if by varying our security parameter R, we managed to get a successful pairing. In this case, if we took a parameter R of 2 centimeters, we could expect pairing to succeed in around 85% cases, while our entropy is around 10.5 bits. And we see the similar results for other cases. Again, if we wanted to have a better trade-off between usability and security, we could, for example, choose a higher security parameter, which would increase the chance of successful pairing, but again, it would lower the security of the protocol. So far, we have only looked at ways to establish a secure connection between two users. We also wanted to see if we could generalize our existing setup and make it work for groups of users. There were two ways that we could go about it. One of them is doing one round of opaque protocol with every other user, while another one is using some generic constructions which transform opaque protocol into round-efficient GPake protocol. For the secret point setup, the first method is perfect because there we would require the users to all look at the same point, in essence establishing the same shared secret, and then it would be really easy to run the same pake protocol with every other user because all of them will have the same secret. For the SecretLine setup, this wouldn't really work because then we would require the users to look at every other user in turn, and they would probably have to do it at the same time. So for that, we would use the second method, and those usually require only the users to exchange some information between neighbors. So if we have the users set up in a circle, we would require the users to look in turn to their left neighbor and then only look at their right neighbor. In conclusion, we could say that AR is already here, and with it, it brought some new ways of interacting with the world. We saw how one can use the spatial mapping capabilities of the devices for new and easy to use secure pairing schemes. More specifically, in our case, we adopted the pake protocol so that it uses spatial secrets and created two ways on how to generate them using typical gaze and tap interactions which are common to AR devices. Our results also indicate that devices can be paired with high probability while keeping the likelihood of a successful attack relatively low. Also, in the future, we expect the performance of the protocols to be even better as the technology advances and as AR devices get better. Thank you everyone for listening.